Hi everyone! In this section I want to come back to Newton's law of universal gravitation before we go on to looking at gravity in orbits in section 5.5. So we've seen this before, but we focused mostly on how gravity acts on objects near the surface of Earth. Remember that the force of gravity is an attractive force between any two objects that have mass. And Newton's law of universal gravitation is here. We have the force of gravity, Fg in newtons, equals G mm, these are the two masses of the objects, one I've labeled capital M and the other lowercase m, in kilograms, over r squared. And r is the center-to-center distance between the two objects, and that's measured in meters. G is called the universal gravitational constant, and it's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So we can notice that the force of gravity depends on the product of the two masses, so larger masses cause a greater force of gravity. And secondly, that it's an inverse square law with respect to the distance between objects. So as if two objects were moved apart, the force of gravity would decrease with respect to the square of the distance between the two objects. Okay, let's look at some examples. Example 13, verify G. Given that the mass of Earth is 5.972 times 10 to the 24 kilograms and the radius of Earth is 6,371 kilometers, determine the local gravitational field strength for objects on the surface of the Earth. Okay, so Newton's law of universal gravitation is here, Fg equals gmm over r squared. I'll use capital M to mean the Earth, and then the lowercase m is the mass of the object, which is near the surface of Earth. Then we've seen before that we use this version, mg, for the force of gravity on objects near the surface of the Earth. So we can equate these two, gmm over r squared equals mg. The object mass will cancel, and we have g equals gm over r squared. So let's check that with the parameters given. G equals 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the mass, 5.972 times 10 to the 24 kilograms. And then that's over the radius of Earth, 6.371 times 10 to the 6 meters squared. And that gives me 9.8136 meters per second squared. So we can see that G, the local gravitational field strength, does depend on the altitude above Earth's surface. This is right at Earth's surface for Earth's average radius, but it will depend on the altitude at that point, and then it would change at any height above Earth's surface. Example 14, calculate the force of gravity on a 50 kilogram person due to A, the Earth, B, the Sun, and C, their 60 kilogram classmate 2 meters away. Okay, so assuming this person is on the Earth, we can use the shortcut form for gravity near the Earth's surface, which is Fg equals mg for part A. So that's going to be 50 kilograms times 9.8 newtons per kilogram, which we just verified, which is 490 newtons for the force on the person due to Earth near Earth's surface. Okay, now the force due to the Sun, we'll use the full form of Newton's law of gravitation. So this is going to be G, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times 50 kilograms times the mass of the Sun, which is 1.99 times 10 to the 30 kilograms. And that's over the radius, or the Earth to Sun distance, which is 1.496 times 10 to the 8 meters squared, which gives me 2.97 times 10 to the 5 newtons. So a much greater force than in part A. And we can keep going now due to a classmate. We have 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, 50 kilograms times 60 kilograms over 2 meters squared, which is only 5 times 10 to the negative 8 newtons. So you can see why the force due to the sun and due to Earth's gravity are so much more significant than the gravity we experience from objects that surround us. Example 15, what is the force of gravity on a 10 kilogram object, A, 100 kilometers above the Earth's surface, and B, 5,000 kilometers above the Earth's surface? All right, so we'll use Newton's universal law of gravitation again. Fg equals gmm over r squared, and I'll use the capital M to represent the mass of the Earth and the lowercase m as the object again. So this r in the formula is the center-to-center distance between the objects. So in this problem it looks something like this. The object is a height h above the Earth's surface, and then to get to the center of Earth we also have the radius of Earth. So r in this equation here is the radius of Earth plus the height above the Earth. And we can plug that right in. You could also solve that separately if you wanted. I've written this out already here. So Fg equals g, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the mass of Earth, which we know now, 5.972 times 10 to the 24 kilograms, and then the mass of the 10 kilogram object, over the total r, the distance between the centers, so 6.371 times 10 to the 6 meters, that's the radius of Earth, plus 1 times 10 to the 5 meters, which is the 100 kilometer height above the Earth's surface. And that's all squared. So you can plug this into your calculator, just be careful with brackets, or again do that denominator separately. And we get 95 newtons for that force. Okay, and now in part B, the object is being moved to a distance of 5,000 kilometers above the surface of the Earth. So the numerator looks the same here. We have g, the mass of Earth, the mass of the 10 kilogram object, and now in the denominator we have the radius of Earth plus 5 times 10 to the 6 meters, which is the 5,000 kilometers above the Earth, and that's squared, which gives overall a force of 30.8 newtons. So we are seeing that decrease as the object moves further away from the center of Earth. Example 16, a neutron star has 5 times the mass of the Sun packed into a sphere 20 kilometers in diameter. Calculate the surface gravity g of this star. So this term, surface gravity, means the same as local gravitational field strength, and which is the same as local acceleration due to gravity. They all mean this constant g. So far we used g equals 9.8 meters per second squared, and that's the value on Earth. Now we want to find this value on this new neutron star. So remember how we found this on Earth. We equated both forms of the force of gravity. So gmm over r squared equals mg, the lowercase m being the object mass or the person mass that's on the surface of the planet. So m cancels and we have g equals gm over r squared. And now we can do this for this neutron star. So g will be 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. The mass is 5 times the mass of the Sun, 1.99 times 10 to the 30 kilograms. And then we have 20 kilometers in diameter, so the radius is half of that, which is 10 kilometers. So this is going to be divided by 10 times 10 to the 3 meters squared, which gives a surface gravity, it's very, very high, of 6.64 times 10 to the 12. And the units here you can see again are newtons per kilogram or meters per second squared. Those are both of the units that work for g that are equivalent here. So we can see that this very massive object that's packed into a small diameter gives a very high surface gravity.